Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. This program unveils the keys to collect phase data and interpret the results to accurately diagnose machinery problems. You'll be able to use the tips and techniques presented here to confirm machinery conditions, including unbalance, misalignment, a bent shaft, mechanical looseness, cocked bearings, and resonance conditions. Other single-channel techniques include tracking phase changes during coast downs or startups to determine the resonant frequencies of a machine, and a brief overview of using phase data for operating deflection shapes, or ODS. Multi-channel applications illustrate the techniques to calculate phase relationships from two simultaneous plots and display a phase spectrum. First, let's look at what phase really is and the ways it is measured. Phase can be defined as the relationship between two events and is usually measured in degrees. For example, let's use this shaft with a wheel fastened to each end and add an unbalanced weight to each wheel in line with each other. As we spin the shaft, the unbalanced weights on the wheels pull both ends of the shaft in the same direction. So both ends of the shaft are said to be moving in phase with each other. If we move one unbalanced weight to the opposite side of the wheel and spin it again, the weights pull on the shaft, but each end is pulling in an opposite direction. Any condition where the wheels are not pulling in the same direction is called out of phase. In this particular case, they're pulling exactly opposite, or 180 degrees out of phase. If we can mount a sensor at each end of the shaft to monitor the shaft's motion over time, they would record a trace of the shaft's unbalance. This trace would be a smooth sine wave for each wheel, but while one wheel is pulling up, the other is pulling down, so that the sine waves are moving exactly opposite each other, or 180 degrees out of phase. When the weights are moved directly in line with each other again, and the trace is monitored for each wheel, they would still be smooth sine waves, but now they are in phase with each other. Recall from another program, Introduction to Vibration Analysis, that the trace is an actual representation of the tire's movement, and that there is a direct correlation of the tire's unbalanced weight to the location on the trace. So when the tire rotated a quarter turn or 90 degrees, the trace moved 1/4 of a full sine wave. 1/4 of a sine wave would be from the top or bottom peak to the center line, or from the center line to the top or bottom. It is important to understand that each revolution of the tire completes a full sine wave, and like the tire rotation, the corresponding sine wave is a full 360 degrees. When one weight is moved 90 degrees and the motion is traced, the sine waves will be out of phase by 90 degrees. With this example, we have been looking at the phase or relationship between the two unbalanced wheels. On a Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. This program unveils the keys to collect phase data and interpret the results to accurately diagnose machinery problems. You'll be able to use the tips and techniques presented here to confirm machinery conditions, including unbalance, misalignment, a bent shaft, mechanical looseness, cocked bearings, and resonance conditions. Other single-channel techniques include tracking phase changes during coast-downs or startups to determine the resonant frequencies of a machine, and a brief overview of using phase data for operating deflection shapes, or ODS. Multi-channel applications illustrate the techniques to calculate phase relationships from two simultaneous plots and display a phase spectrum. First, let's look at what phase really is and the ways it is measured. Phase can be defined as the relationship between two events and is usually measured in degrees. For example, let's use this shaft with a wheel fastened to each end and add an unbalanced weight to each wheel in line with each other. As we spin the shaft, the unbalanced weights on the wheels pull both ends of the shaft in the same direction. So both ends of the shaft are said to be moving in phase with each other. If we move one unbalanced weight to the opposite side of the wheel and spin it again, the weights pull on the shaft, but each end is pulling in an opposite direction. Any condition where the wheels are not pulling in the same direction is called out of phase. In this particular case, they're pulling exactly opposite, or 180 degrees out of phase. If we can mount a sensor at each end of the shaft to monitor the shaft's motion over time, they would record a trace of the shaft's unbalance. This trace would be a smooth sine wave for each wheel, but while one wheel is pulling up, the other is pulling down, so that the sine waves are moving exactly opposite each other, or 180 degrees out of phase. When the weights are moved directly in line with each other again, and the trace is monitored for each wheel, they would still be smooth sine waves, but now they are in phase with each other. Recall from another program, Introduction to Vibration Analysis, that the trace is an actual representation of the tire's movement, and that there is a direct correlation of the tire's unbalanced weight to the location on the trace. So when the tire rotated a quarter turn or 90 degrees, the trace moved 1/4 of a full sine wave. 1/4 of a sine wave would be from the top or bottom peak to the center line, or from the center line to the top or bottom. It is important to understand that each revolution of the tire completes a full sine wave, and like the tire rotation, the corresponding sine wave is a full 360 degrees. When one weight is moved 90 degrees and the motion is traced, the sine waves will be out of phase by 90 degrees. With this example, we have been looking at the phase or relationship between the two unbalanced wheels. On a machine, the phase is normally measured from a fixed or reference position on the rotating shaft to the peak of vibration at the sensor. The reference position can be a keyway or any other location, but is most often simply a position marked with reflective tape. A phototack such as this is then used, which sends a light beam to the rotor. When it strikes the reflective tape, the light is sent back to the phototack, which then sends a signal or pulse out to an analyzer. The tack pulse is then used as the reference location and speed of the shaft. The tack signal generates a pulse similar to a square wave. Notice it is not a true sine wave, but is flat for a brief duration equal to the time the tack sees the reflective tape. The time from one peak to the next is the time between pulses from the reflective tape each revolution of the shaft. Some systems allow the tack pulse to be displayed directly on a vibration waveform, which can give you a clearer picture of the phase relationship. When the vibration sensor is moved to the opposite side, we would expect the relationship to change about 180 degrees. And as we expected, the tack pulse is now at the opposite, or in this case, the negative peak of vibration. When the sensor is moved to another location 90 degrees away, we expect the phase to change by 90 degrees also, as this one does. There are some important concepts to remember. First, phase is a relationship of two events. One is usually a vibration sensor, and the other is usually a tack pulse from a piece of reflective tape mounted on the rotor. Since the signal from the phototack is used as the reference, It should not be moved anytime during data collection. Only the vibration sensor should be moved from one location to another. The second point is that the relationship is usually measured in degrees. Thirdly, a movement of the sensor radially should produce a shift in the phase by the same amount. If the phase does not shift by the same or similar amount, it is evidence of another problem that is discussed in a later section of this program. We have been using a multi-channel analyzer to view the waveform and illustrate the concepts of phase and phase changes. However, phase measurements can be displayed in degrees using a single-channel analyzer. The signal from the phototac is input here, while the vibration sensor is mounted the same as for routine data collection. The mode in the analyzer that recognizes and calculates the phase angle is called peak phase. That is, it measures the peak of the vibration and records its occurrence relative to the tac pulse. During the measurement, the screen displays the amount of vibration and the phase angle in degrees. Although we can't see the waveform and tac pulse here, the phase is displayed in actual numbers without having to estimate the value. When the vibration sensor is moved 90 degrees, the phase angle displays the corresponding change. Now move or roam the sensor to various locations on the machine and record the phase angle to get an accurate picture of the machine's movement. For example, when we measure the phase on a machine in a vertical direction across the coupling, if the phase is about the same, then the machine is moving together. But if the phase readings are about 180 degrees out, it indicates a misalignment condition. More examples and rules of thumb are shown in the section Static Phase and Machinery Conditions. As you are making these phase measurements, the phase angle should be steady as it is here. Some machines have dynamic forces due to process variables that may cause the phase to fluctuate some. When the phase stays within a 30-degree swing, it is usually considered steady. However, another cause of an unsteady phase is the presence of other energy being included in the measurement. View the spectrum to ensure there are no peaks close to the 1 times peak, because they may interfere with the measurement. The phase measurements use the tac pulse as the reference frequency and only monitor the vibration in a narrow band around the tac pulse frequency. On this belt-driven fan, there are at least 2 frequencies that could be close to the motor speed. One is the fan speed, depending on the belt sheave sizes, and the other is a multiple of belt frequency. The motor speed is the peak at 1,685 cycles per minute. 2 other peaks are nearby. One is approximately 1,865 CPM, and the other is approximately 1,400 CPM. If the specified bandwidth is too wide, it will include peaks of vibration from more than one frequency, creating a very erratic and unstable phase. When the bandwidth is set to 10%, it means that all the energy within a bandwidth equal to 10% of the tac pulse frequency will be included. For example, if the tact speed from the motor is 1,685 CPM, then 10% of that is 168.5 CPM. So the monitored bandwidth is 168.5 CPM wide and will include all the vibration peaks in this band. This means the peak at 1,865 CPM may be included in the data, and since its peak of vibration is a different frequency from the actual tact motor speed, it will cause the phase to be very unsteady and move all around, not just fluctuate within a 30-degree window. Reducing the bandwidth to include only the peak equal to the tact speed stabilizes the phase reading and provides a better picture of the machine's movement. Sometimes the phase may still fluctuate in a 30-degree window and may be unacceptable in applications such as balancing that require a precise phase reading. This fluctuating phase reading can be averaged for a few minutes until it is steady. However, for normal phase readings, the averager should be turned off to see the instantaneous phase angle. Since the phase angle tells the direction of movement, it can be displayed as a vector when it is coupled with the amount of movement. A vector is a graphical representation of amount and direction. Some analyzers have the capability of graphically displaying the vector. The display can show the instantaneous phase, the average phase, as well as the limits of its movement. This provides a good picture of the movement as the vibration sensor is moved from one measurement location to another. We have shown the usefulness of these measurements and how they are a relationship between two events. However, you need to know that there are two methods or conventions in industry for calculating phase. One convention uses the tach pulse as the reference point and begins counting the angle as the rotor turns, 10, 20, 30 degrees and so on around the rotor to the peak of vibration. This convention, which measures the reference pulse to the peak of vibration, is called true phase. Another convention measures from the peak of vibration to the tach pulse and is called reverse phase. All CSI equipment uses the true phase convention. When balancing, you will need to know which convention your system uses so that correction weights will be located correctly. But for most general phase measurements, it is not necessary. Other tools that can be used for making phase measurements are a strobe light and a vibration sensor. The signal from the sensor is sent to the strobe light, causing it to flash at the rate of the vibration. In order to use this method for diagnosis, either the signal must be dominant at shaft turning speed, or it must be filtered to cause the strobe to fire at the shaft speed. The rotor must be marked with either a reference mark or the angles. When the rotor has a reference mark, then the phase angle must be read from stationary marks from 0 through 360 degrees. When the rotor is marked with the angles, then use a fixed point on the machine as the reference point. Then, as the sensor is used to roam the machine, the phase angle can be read directly from the rotor and the machine, and then manually recorded. Whether you use a strobe or a photo tach and analyzer, the rotor must be marked. For most of our examples, we will use the photo tach and an analyzer. Phase measurements can be a good analysis tool. To ensure they provide the best information, the phase should be steady. It may be necessary to view the spectrum to make sure the bandwidth does not include other peaks that are close to running speed and cause erratic phase readings. Remember to keep the photo tach in the same position for all the phase measurements on the machine. Phase analysis can be used for two specific operating conditions. One is a static condition. That is, the machine is operating in a steady state with only small fluctuations in speed and load. The other is a transient condition. That is, the machine is changing in either speed or load. The most common transient application is during a startup or coast down. But here, we will use static phase measurements to diagnose machinery conditions such as unbalance, misalignment, bent shafts and cock bearings, mechanical looseness, resonance, as well as a brief overview of operating deflection shapes. There are 6 radial and 6 axial phase comparisons used in diagnosing machinery conditions. The radial comparisons are horizontal to horizontal for each component, vertical to vertical for each component, horizontal to horizontal across the coupling, and vertical to vertical across the coupling. The axial comparisons are from component to component across the coupling, end to end of each component, and side to side for each component. Because there are so many variables, it is sometimes easier to understand the machine's movement when the phase angles are recorded on a sketch of the machine. Then, when making the comparisons, draw arrows to indicate the relative direction of movement. When diagnosing an unbalanced condition in a machine, we are usually referring to the unbalance of a component. That is, either the driver, such as a motor, or the driven unit, such as a pump, fan, and so forth. Like the unbalanced wheels that pull on the shaft, unbalance in the machine component pulls the shaft, generating a bump each time the shaft turns. This type of unbalance produces movement in the same direction along the shaft. Therefore, phase readings in the vertical direction from one end of the component to the other will be in phase. The horizontal readings on the component should also be in phase. And axial readings across the coupling should be in phase. As a rule of thumb, when diagnosing machinery conditions, most actual machinery phase measurements will not be exactly in phase or exactly out of phase. but should be within 30 degrees. Phase measurements from the horizontal to the vertical position at the same bearing location should shift 90 degrees, since the sensor is moved 90 degrees. These conditions are typical of a static unbalance condition. Static unbalance is a condition when the rotor is unbalanced, so that when it is at rest in a frictionless bearing, the heavy spot will swing to the bottom. Another type of unbalance may actually be statically balanced, so that the rotor will stay in any position when it is at rest, but when it is spinning, it exhibits unbalance. This is because each end of the rotor is unbalanced. The unbalance amount is the same at each end, but in opposite directions, so that the rotor is balanced while it is still. When the rotor is spinning, centrifugal force causes the unbalanced weights to pull on the rotor. In this case, they would pull in exactly opposite directions. This type of unbalance is called couple unbalance. So for a couple unbalance, the vertical to vertical readings or the horizontal to horizontal readings would be 180 degrees out of phase. Any combination of static and couple unbalance is referred to as dynamic unbalance. The phase change from vertical to vertical or horizontal to horizontal could be any combination depending on the amount and location of the unbalance. For dynamic unbalance, couple unbalance, and static unbalance, the axial readings across the coupling should be in phase. Again, in phase is normally considered to be within 30 degrees. Another consideration in phase measurements, especially in the axial direction, is the direction of the sensor. Most of today's sensors, both accelerometers and velocity sensors, use pressure-sensitive crystals as the internal sensors. When the crystal is squeezed due to the impact of the vibration, a signal is generated and sent to the analyzer as waveform data. For most sensors, the impact of the vibration toward the sensors is the positive side of the waveform. Movement away from the sensor is the negative side of the waveform, or 180 degrees away. Because of this, there is a difference of 180 degrees when the sensor is flipped from one side to the other. So it is very important to take into consideration the sensor orientation, especially on axial measurements. If the orientation is not the same, be sure to subtract 180 degrees from the measurement to correct for it. In another program on the process of alignment, we pointed out that there are two types of shaft misalignment. One is angular misalignment, and the other is offset misalignment. In angular misalignment, as the shafts rotate, the coupling firmly holds the ends, causing them to bump once in the radial direction as they attempt to correct themselves. The rotation forces the shafts to push away from each other in the axial direction. Because of this, phase readings in the vertical or horizontal direction from one end to the other will be 180 degrees out of phase. Across the coupling, there is no phase shift in the horizontal or vertical direction. However, in the axial direction, there is a 180-degree change across the coupling. Remember to account for the direction of the sensor for these axial readings. When shafts have an offset misalignment condition, the coupling pulls one shaft one direction, and the other shaft the other direction radially, forcing them to match up. This condition produces a 180-degree phase shift across the coupling in the vertical or horizontal directions. The axial readings across the coupling are in phase. Because the coupling is pulling on the shaft, the feet closest to the coupling act as a pivot point. The location of the feet relative to the measurement point then affect the vertical or horizontal readings across the couplings so that they may be in phase or out of phase. In all these alignment measurements, be sure to allow a 30-degree difference for determining in phase and out of phase conditions. Bent shafts and cocked bearings can have the same phase characteristics under certain conditions and therefore may be difficult to differentiate. Bent shafts fall primarily into two categories with very differing phase characteristics. One is a bend in the rotor between the bearings. The other is a bend in the rotor at the coupling. A rotor which is bowed between the bearings actually has an unbalanced condition, but exerts axial force on the bearings. The bend causes one side of the rotor to be longer than the other, forcing the bearings out during part of the rotation and lets them flex in for part of the rotation. This makes it appear as if the ends of the shaft are moving in opposite directions, while for a straight shaft, the ends are moving together. The phase data for a bent shaft, then, will be 180 degrees out in the axial direction from one end of the shaft to the other. Be sure to account for the direction of the sensor. Because of the axial movement associated with a bent shaft, the axial direction provides the most information. 4 other axial measurements should be made. Assuming a clock face over the end of the bearing or machine, the measurements should be made at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions. A cocked bearing will exhibit approximately a 180-degree difference from the 12 o'clock position to the 6 o'clock position. 180-degree phase shift will also be present from the 3 o'clock position to the 9 o'clock position. Again, these measurements are normally within 30 degrees. When a shaft is bent at the coupling end, it moves in the same way as a combination of angular and offset misalignment condition. The phase data will have a 180-degree change across the coupling in vertical to vertical or horizontal to horizontal measurements. The axial measurements across the coupling may have any phase relationship depending on the coupling type and the amount the shaft is bent. A bearing cocked on a shaft has the same phase characteristics as a shaft that is bowed between the bearings. As the shaft rotates, it tends to force the cocked bearing to correct its position. Because it cannot be forced into a correct position, the bearing can actually force a bend in the shaft and exhibit characteristics similar to a bent shaft. The axial direction will produce phase data 180 degrees out from side to side or top to bottom of the bearing. Mechanical looseness can exhibit both directional and erratic phase characteristics. The directional phase is associated with loose bolts, mountings, base plates, and other non-rotating components. Erratic phase readings are normally associated with looseness in the rotating elements. When a component is loose at the mounting positions, the foot tends to hammer against the bolts and the base plate. Measure the phase on the bolt, the foot, the base plate, and even the floor to determine the movement. A loose mounting produces a 180-degree phase shift from the bolt to the foot, from the foot to the base plate. If there is no phase shift between two of the components, such as the floor to the base plate, there is not a looseness problem there. Erratic or unstable phase measurements can be associated with rotating element looseness. During normal phase measurements, if the phase is very unsteady, not simply slowly rotating or staying within a certain window, then check the spectrum for peaks near the 1 times peak and verify that the bandwidth is narrow enough to include only the 1 times peak. Also check for a looseness spectral pattern, that is, multiple harmonics of the turning speed peak. The waveform of a looseness condition will have a very non-repetitive pattern due to the random impacts as the rotor is rattling around in the mountings. During a balance job, the phase readings may be steady and then become erratic after a correction weight is applied. This is because a looseness condition existed at the beginning of the balance procedure, with the force of unbalance pulling on the rotor, holding it in a firm position and masking the looseness. Once the force due to unbalance is reduced substantially, the rotor exhibits looseness as the dominant condition, which then minimizes the effectiveness of further balancing. When performing phase analysis on a machine, remember that looseness can exhibit a directional phase of 180 degrees between components and erratic phase indicating rotating element looseness. In another program, Resonance Detection, we used a tuning fork to illustrate the fact that everything has at least one resonant frequency and that resonance can amplify the forcing frequency by more than 10 times. Another characteristic is that the phase changes as the machine's speed is increased or decreased to pass through the resonance frequency. This phenomena of a 90-degree phase shift at resonance provides another tool to detect a resonance problem. For example, normally when the sensor is moved from a horizontal to a vertical position, there should be a corresponding phase change of about 90 degrees. However, if the phase changes 0 or 180 degrees, it indicates a directional resonance condition. The 90-degree shift due to resonance causes what should have been a 90-degree change to be either a 0 or 180-degree change. Throughout these examples, we have been ignoring the vibration amplitude. However, to determine which of these directions has the resonant condition, it may be necessary to compare the amplitudes of both readings. A good rule of thumb is, if the amplitude ratio between the two radial measurements is 1:3 or greater, it is a good indication of a resonant condition. It is not uncommon for one to be 10 or more times higher than the other. The measurement with the highest vibration amplitude is the location of the resonant condition. When this phase condition exists, then inspect the component for integrity, such as cracked wells, which affect the resonant condition. There have been many instances where cracked bearing pedestals and supports have been re-welded, and upon restart, the machinery vibration returned to acceptable levels. Another indication of a possible resonance condition is erratic phase readings. Depending on the stiffness of a machine, the resonant frequency may have very little damping. This means that if the machine's speed excites a resonance, even small changes in speed drastically affect the phase, causing it to be very unsteady. If this condition is suspected, perform tests to verify whether it is resonance. In summary, resonance can be detected with phase analysis due to its phase characteristics, which can be directional or very erratic. An operating deflection shape is, as the name implies, a graphical representation of a machine's motion at operating speed. Since phase measurements provide both the direction and amount of movement, they can be used for multiple points on a machine to illustrate how it is moving. Many phase measurements are required, and they must be entered into a software program to animate the measurements. Make a grid sketch of the machine locating the specific points for making measurements. Record the phase readings for each of these points. The operating deflection shape can then be animated and turned to see how each element is moving. From this, you can get an idea of the flexing taking place in the machine. Static phase measurements can provide much information about the machine's condition, and when multiple phase data points are input into a software program that animates the data, you can actually see the movement that is taking place in the machine. Static phase measurements provide another tool for diagnosing many machinery conditions. Remember that because phase measurements provide amount and direction, they can be displayed as vectors to show the machine's motion. Use the 6-phase comparisons in the radial direction and the 6-phase comparisons in the axial directions. Be sure to take into consideration the orientation of the sensor. The directional phase comparisons, as well as some erratic phase conditions, point to specific machinery faults. All of these measurements have been using the 1 times shaft speed and filtering out all other frequencies. However, a multiple of the takt pulse frequency can be monitored by entering that number here, which then invokes a filter around that band. This feature is valuable for some applications. For example, if a horizontal measurement has a high 3 times peak, but the vertical is very low at the 3 times peak, then monitor the third order and compare the phase relationship at this frequency. There should be a 90-degree phase shift between the two. But if there is a 0 or 180-degree change between them, then a resonant condition exists. In this section, we have addressed unsteady phase and erratic phase. But there is another problem that sometimes occurs, especially on motors, and that is walking phase. A walking phase is one that moves through the 360 degrees of the circle. It is usually fairly slow, so that at first the measurement may seem fairly steady, but over the period of a minute or two, the phase has walked the entire circle. This phenomena occurs when two dominant peaks are close together, within 20 CPM, such as electrical line frequency at 3600 CPM and a shaft speed of 3595 CPM. Usually, the closer the two frequencies, the slower the phase walks. On frequencies this close, it is sometimes impossible to separate them to include only shaft speed. Another powerful analysis tool is tracking phase through transient machine conditions. Transient conditions are those that are changing over time, such as during a startup or coast down. The data collected can then be displayed in Bode plots or a Nyquist plot. The Bode plots are the amplitude versus RPM and the phase versus RPM. A Nyquist plot combines the two plots to show the amplitude and phase vector for every machine speed. The coast down data provides very good information for determining resonant frequencies because as the shaft RPM crosses a resonant frequency, the vibration amplitude is recorded as well as the phase. Details for setting up and collecting startup and coast down data are included in another program, Resonance Detection, and are not repeated here. Here we will show examples of coast downs and interpret the results. This coast down plot has two high areas of vibration that at first seem to indicate there are two resonances. However, when viewing the phase plot, the phase changed at one of the high amplitudes, but not the other. Without a phase change, the machine did not go through a resonance. The high vibration at this frequency is from some other source. In areas where multiple machines are running, the high vibration could actually be from another machine. In this example, the high vibration is from a severe unbalanced condition in a nearby machine. We know that there should be a 90-degree phase change as the RPM moves from one side of resonance to the resonant frequency. Then there is another 90 degrees as the RPM continues past the resonant frequency. However, sometimes the phase plot will show a 360-degree phase change, and the amplitude versus RPM plot looks normal for a resonant condition. This occurs because two systems are in resonance at the same frequency. A typical example is when there are several machines of the same type nearby, such as a row of identical pumps or fans. A coast down may indicate a good phase shift at a particular frequency, and we would expect a high vibration at the same frequency. However, the amplitude versus RPM data does not have an increase at that frequency, but may even have a low area or hole. This indicates the presence of some mechanical damping, such as a tuned dynamic absorber. The dynamic absorber is designed to remove the vibration at a particular frequency, and this indicates it is doing a good job. When there are two phase shifts, it indicates there are two resonances in the system. Both phase shifts will be in the same 180-degree hemisphere. These Bode plots can reveal good information about the machine conditions, especially the resonance frequencies and the amplification range. The amplification range is the frequency range where the vibration is amplified due to resonance. The Nyquist plot is a polar representation of the recorded phase and amplitude. Each point is then the vector location of the unbalanced amount and direction for each RPM during the coast down or startup. The loop should be 180 degrees of phase change from one end all the way around to the other, with the resonance frequency being at the halfway point. There may be other circles with a 180-degree phase change along this circle, which are other resonances in the system. To collect good phase data without holes or gaps for machines with quick startups or coast downs, increase the bandwidth to get faster samples and data. Phase data from transient conditions, such as coast downs or startups, provide information about resonant conditions and frequencies that may be difficult to acquire by other means. This information can help you in determining appropriate operating speeds and residual unbalance. Multi-channel analyzers can perform the same functions as a single-channel analyzer and more. They have the ability to track and display two signals at the same time and then compare them, even drawing a phase comparison between the two. Earlier in this program, we used a multi-channel analyzer to display the tach pulse directly on the waveform. As we roamed the machine with the sensor, we could see clearly the phase change from point to point. However, for phase analysis, probably the most powerful technique is called cross-channel phase, which allows you to use two or more vibration sensors for phase measurements. A big benefit to this is the machine process does not have to be interrupted to mark it with a reference tape or be pre-marked with the phase angles, but instead uses the actual vibration data from one sensor as the reference and compares it to the data from another sensor. Essentially, it performs the same function we illustrated with the two sine waves from the unbalanced wheels. That is, it compares the peaks for a particular frequency to determine if they are in phase or out of phase. The time difference is calculated to determine the exact phase relationship between the two. The waveform energy may seem to be very busy and intimidating for us to perform any calculations, but the analyzer can display the data as a spectrum. Then we can select a particular frequency of interest and have the analyzer display the calculated phase relationship. Notice that we can select any frequency in the spectrum for the phase comparison. Because this capability is here, there is also the ability to display the phase relationship for every frequency in a phase spectrum. This spectrum has frequency as the x-axis, but has phase in degrees as the y-axis. Now we move the cursor to a particular frequency on the reference spectrum and read from the phase spectrum the corresponding phase angle. In order to use this cross-channel phase effectively, certain setup considerations must be made. First, the two sensors must be using the same units, such as G's. Secondly, the sensors must be in phase. That is, they must read the same phase angle for a given point. To check for this, place the two sensors side by side on a machine and check the phase between the two. They should read exactly the same or within 10 degrees of each other. Now select one sensor as the reference and the other as the roaming sensor. In some multi-channel analyzers, the X channel must be the reference. In systems using A and B channel references, the A channel typically is the reference channel. Then make the measurements, storing the data for later retrieval and analysis. With the multi-channel instrumentation, the same 6 radial and 6 axial comparisons should be made as with a single-channel analyzer. In making these measurements, two significant differences exist between a single channel and a multi-channel measurement. First, the reference is portable. That is, it may be moved depending on the need. So for a horizontal to horizontal comparison, it must be in one of the horizontal positions. And for a vertical to vertical comparison, it must be moved to one of the vertical points, and so on. The second difference is the multi-channel has the ability to look at any frequency of interest. Another advantage is the data is stored as spectral and waveform data, allowing you at your convenience to perform any analysis, including cross-channel phase, which is only one of many multi-channel functions. A case history involving multi-channel phase data to solve a vibration problem on a high-pressure centrifugal pump illustrates the value of phase analysis. The pump header repeatedly cracked, causing a shutdown of the manufacturing process. A temporary brace was installed to help remove the strain on the header, but it cracked again. No other work has been done on the machine, and the process, speed, and machine configuration were not changed. Since cracked wells are typically indications of resonant frequencies excited from some other forcing frequency, there must have been internal changes in the machine to generate a forcing frequency. Now it is the job of the analyst to determine the resonant frequency and the source of the problem. Initial data was collected on the pump body in the vertical and horizontal directions. Amplitudes in the horizontal direction on the pump housing exceeded 50 Gs. Amplitudes in the horizontal direction on the coupling end of the motor at motor shaft speed were in excess of 1.2 inches per second. The apparent problem frequency identified during this data collection process was the running speed of the motor, 59.5 hertz. New questions now arise. Is the 1 times turning speed of the motor the cause of the problem? If so, what change occurred in the machine to cause this? Where are the resonant frequencies? Since the data indicated that 1 times turning speed was the possible cause of the problem, the decision was made to gather impact data to determine the resonant frequency. Phase data was provided using a multi-channel analyzer. The data from the impact test in the vertical direction does not coincide with the 1 times turning speed of the motor from the initial data. When the horizontal impact data was gathered, it became apparent that the 1 times turning speed was exciting the resonant frequency in the horizontal direction. In an attempt to find the changes in the machine's integrity, the analyst found a significant phase shift, 143 degrees, from the horizontal to horizontal position across the motor to the gearbox coupling at 1 times turning speed. The 143-degree phase shift across the coupling indicated a misaligned or locked coupling. All other measurements were normal. Since amplitudes exceeded 1.2 inches per second in the horizontal direction and the vertical to horizontal comparison did not indicate an unbalanced condition, the coupling was considered to have a fault. Upon inspection, the coupling type, which should have been lubricated, had no lubricant, causing the coupling to lock up in a misaligned position and forcing the extreme motion in the machine. Replacing the coupling resulted in a reduction of vibration by a factor of 10. The phase data provided the ability to identify the resonant frequency and the source of excitation. These measurements could have been taken with a single-channel analyzer. However, the reduced time to collect the data and ability to have the same time reference for the comparisons made the use of the multi-channel analyzer the tool of choice. Phase and phase analysis are powerful tools that can aid you, the analyst, in making accurate diagnosis of machines and machinery components. Because static phase measurements indicate a machine's motion and particular frequencies, such as operating speed, you can use it to confirm machinery conditions, such as static and dynamic unbalance, offset and angular misalignment, a bent shaft and cocked bearing, mechanical looseness and mounting, rotating element looseness, and resonance. The phase data can be entered into an ODS program to animate the motion at operating speeds. Transient phase data provides the necessary information about resonance frequencies and can be displayed as Bode plots or a Nyquist plot. Multi-channel phase can provide the phase relationship at every frequency of the spectrum. While many areas have been covered, we've only highlighted the most common phase characteristics and measurement practices. We realize that unique design and applications necessitate special considerations for phase measurements and analysis. Thank you for joining the thousands who recognize CSI training as leading industry with quality information, instruction, and application of PDM and RBM techniques. Whether you use single or multi-channel analyzers for the collection and analysis of phase data, we are confident that the application of these tips and techniques will help you succeed in phase analysis projects. We look forward to assisting you achieve success in your future endeavors.